Right, good evening everybody, and welcome to tonight's inaugural lecture by Mike O'Boyle. And in particular, I'd like to welcome Mike's family and his colleagues, both from academia and from industry. You're all very welcome to the main event of tonight. So Mike was born in New York and gained his BSc in Maths and Computer Science from Aston University. He then studied at Manchester for his MSc and PhD in Computer Science, and then worked in that city from 91 till 96. And that's when he saw sense, and he moved to Edinburgh as a lecturer, and he's remained here ever since.
That's right.
He gained a personal chair in 2006, so I have to say this is a long-awaited inaugural lecture. You have had plenty time to write it, plenty time to practice it, so no pressure, Mike.
No pressure.
So, currently, Mike is the director of the Institute of Computer Systems Architecture, and in research, he poses his main question: how can computer technology best exploit the potential of high-performance architectures? Now, I know you all expect a little piece of other information about Mike, so my other information about Mike, away from his involvement here in informatics, is that you are a fanatical climber, I'm told. And he was the first person to climb 2 mountains in the, now I don't know this, is it the
Kangalushiak.
Oh, Kangalushiak, oh, see, I would never have got that, region in East Greenland. And I think you've got to name the mountains.
Yes, one's Mont Brigitte, after my wife, and the Peak of the Beloved Sons, after the 2 boys that are here.
So isn't that nice? I think that's really cool. Well done, Mike. So I'm now going to ask you after that, because I can't top that one. So I'm going to ask Mike now to give his inaugural lecture, Return of the Silver Bullet, or Avoiding Groundhog Day. Mike,
right.
Thank you very much.
Thank you very much, Leslie. So thank you for the very generous introduction. Yes, it has been many years since I should have done this, but 1 or 2 things have changed in the computer systems area since those days, so perhaps it's been worth the wait. So an alternative title for this talk is actually Auto-parallelisation Reloaded. It's been an area of much debate in the 70s, 80s, 90s. It went out of fashion for a while, and it's back with a vengeance. What can we do differently? Although this is an inaugural lecture, the truth of the matter is actually I'm just one member of a team, actually a very small member of a team. And these guys did really all the work. So thank you for all your help over the years. I'm just taking the credit for your work, but these are the guys who actually did it. So when I put this talk together, I talked to various members of my friends, family, and beyond. And I was asked a really devastating question that all academics fear. And what is that question? I said, what do you actually do? You know? Well, I go to a building every day of the week, sit there for a while, stare out the window, type, drink a lot of coffee, argue about how things are bad, and then go home again. So, but what's the sort of technical content beyond all that? Well, what I really do is a thing called compilation and parallelization. So I'm going to spend the next couple of slides trying to describe those things in kind of layman's terms before we go off into the merry word of academia. So, compilation is really a translation process. Let me explain what I mean by translation. So say you're a human being up there, and you want to ask the question, how high am I in meters? And you want this thing down in the corner of this very sexy HP server computer to actually do that for you, calculate that thing for you. Well, unfortunately, it doesn't speak English. It speaks ones and zeros. So what you have to do is put that in a form that this machine can understand. Can you translate it? The first stage is to write that in a thing called a program. So here's our very high-level program. Your height in meters is really your height in centimeters divided by 100. I think that's right. I'm sure there's some corner cases I missed. But that's basically the thing we want to see. Then once you've got it in that kind of high-level language, it still looks quite a lot different to that thing down the bottom. So this is where I step in, and my colleagues. We basically translate that high-level thing down to noughts and ones. And that's what we do. Compilation is really a translation process from questions to forms that machines can understand. However, if it was just that, it wouldn't be a very long talk or a very interesting one either. There's a bit more to it than that. So let's ask a slightly more difficult question. Will it rain tomorrow? And that's actually quite a difficult question because you have to model the weather, and that's a bit more complicated than one line of syntax. It's very complicated, in fact. We still want to get this machine down the bottom, so we could write it in a programming language that looks something like this, horrendous, but it's real, it's called C, and that people write programs in it to actually try and calculate answers. And then we've, yet again, got to try and translate it into a form that the machine will understand. However, the trouble is, there's more than one way of doing it. There's well, at least 4, maybe 5. There's actually quite a lot of ways to do it. We tried enumerating all the ways, and after a little while, it gets quite large. In fact, even for small programs, there are size 10 to the 80 different ways of translating it. And for large ones, there are more ways to translate it than there are known particles in the universe. It's a big problem. The question is, which is the best one? So it could be best, could be the fastest, which we're going to concentrate on today. It could also be smallest to fit inside your phone, or coolest so it doesn't burn your hand. Lots of different things. So in some sense, compilation is really not translation and an optimization problem. You've got to pick the right one. Now, there are many, many different examples out there, many different forms. Can you pick the one that's the best for you? And that's what today's lecture is about, picking the best one. There's also another part to this thing. This is just the compilation side. I said it was also contained a thing called paralyzation. Now, paralyzation, for us, turns up in the following form. We still got our question. We want to find out that complicated question, how tall am I? And I mean, it's OK when you've got to try and run it on one machine, even though it's very difficult to get the right version we just saw. But what happens when you have more machines out there? You somehow got to chop all this work to make sure that all those machines are kept busy and you can do the job fast. So for me, this area of optimization and parallelization combined together is what we call auto-parallelization, and it's the focus of today's talk. So that's what my research is in a nutshell. If that's, for many of you, that's going to be enough, or you want to hear about it, you can leave now, but there's a bit more detail behind the slides coming up. So I've been working in this area for quite a long time, compilation. So I remember chatting to my supervisor, and his name will remain anonymous for now, being checked on the web, and he said, basically, this area is dead. You should just go home. In 5 years, we're all going to sort this out. Another guy, a famous guy, Cook, said in 1990, we've got this problem solved. There's no more problems out there. And I remember talking to some chemists in Manchester saying, yeah, you might have some ideas, but I don't like you doing what you're doing. I want to do it. Stop it. So back in the 90s, I was told to go and change my mind, to do something different. I remember in 2005, I got quite a nice conference as well. So we did this really great elegant idea how to optimize code for hardware. And we said, this conference is not for smart compilers. You should stop what you're doing. We don't like it. Go away. But in some sense, looking at one of my colleagues, it's the perfect research topic. It's impossible to prove and get it right correctly, to get it optimal, and it's always undecidable, so there's always room for improvement. So what I would say is, my supervisor said it's dead in 5 years. Actually, it's going to run forever. So if you want a long-term research career, we can always promise one more result from one more paper. It's the subject for you. View of parallelization. This is my favorite quote. I've had many papers rejected over the years. I'm sure you've had one or two. Back in 1997, said, who cares about parallelism, right? It's been done, right? It's been done on the subject. What about Java? Java's cool. And that literally is, I mean, there was a couple of words, but that was exactly the quotation I had. So yeah, I should have done Java, right? Then, of course, it's all been done, right? Well, then in 2005, the industry's in a bit of a panic. They don't know how to do it anymore. So we've gone from it's all been done, why don't you look at Java, to we don't know how to do it, what we're going to do. So we often see this kind of thing in cycles in computer science. Problems come round and round again, and in particular, that's why we have the reloaded statement in the title today. So, parallel computing compilers. Can we avoid Groundhog Day, doing the same thing over and over and over again and failing? So that's today's lecture. Can we answer that problem? Well, for those of you who like to have things in sort of more explicit, this is the high-level overview of the talk. With a grey past, we failed. Got a bright future. Give me the grant. Right? We're going to solve the problems. So let's give a little bit more detail behind that. So here's the structure of today's talk. Parallelism past, we talked about the silver bullet. The silver bullet was going to solve all our problems. And in actual fact, it failed. And we're trying to work out why we fail. It's important to work out why you fail, because you can't change and succeed next time round. And then talk about the partings of the way of the community. We used to be one big happy family back in the 90s. We went our different way. And now I'd like to explain why we did that and what compilers did next. And then I want to talk about a methodology revolution, which we've been part of, and the data-driven optimization that's changed the way we do things in compilation. And then I'm going to talk about the present, talk about two-stage view of solving today's problems, and go beyond just parallel computing to a thing called heterogeneous computing, where machines get even weirder than they are today. So that's the structure of today's talk. So this is the good old days, back when machines were machines. So this thing here will cost you the price of an aircraft carrier. It was expensive. It's an old Cray 1, very, very precision engineering element. So what you did, you wanted that thing there was go very fast. And what you wanted to do is take your dusty deck codes that came in, probably not in cards like this, but I'm trying to get the effect of old technology. And you somehow want to get that running on one of those things. How do you translate your programs to run on this thing here? So who's going to save us to get our dusty deck code to run on these shiny new machines if you don't know how to do it? Well, the answer is, of course, the silver bullet, right? So otherwise known as auto-parallelization. It was going to take your code here, you can sit at home nicely, press the button, and it can translate your code to run on the parallel machine. And that's what we wanted to do. And that was the promise of many of the researchers in the 70s, 80s, and 90s. We're going to solve this problem. So what it's going to do, it's going to solve everything automatically. Just putting enough analysis into unpicking the code, a bit more clever, deeper semantic analysis of the program, some more transformations, we'll be able to work out what you really meant and translate it to this new parallel machine. One more research grant will get us there. I'm sure I wrote that somewhere. But the question is, did it work out that way? And I guess the answer is, we know the answer is no, it didn't work out that way. There were one or two problems, of course, that we have to reflect on. I want to know, what are those one or two problems? Right. Well, I'll give an example of some of the successes before we start digging down into the depths of the failures. Here we have some sort of sequential code, something written in Fortran. It's basically array reduction. The compilers at that time could actually transform it and get this parallel code over here. So they were quite clever. They did really, really well. And they could get quite good performance. So here the programs on the bottom, and this thing's called speed up. The bigger the bar, the better. That means it goes how fast do you go? So some code you go 8 times faster, some are a bit slower. So in other words, these compilers did really well. So were we loved? Well, not really. The trouble is, programmers could do better. So whilst we could get a speed up, say, of 8.7 on this old machine, a program would get 10.6 rats. Some other programs here, we could only do 2.2, and they were getting 16 times better. So in other words, we weren't as good as the programmers. So it doesn't matter how clever you are. If you're not as good as a human, why invest in your technology? So part one of the downfall is parallel computing back then was an elite. And there's elite programmers. And they were too hard to impress. They were just the top of the pyramid. So in other words, we'd rather be down here where people don't really know much about computers. We can beat them easily. When you're trying to compete with these guys, you're never going to win. So that was a really hard competition. So we picked the wrong fight, basically. It was more to our failure than others than this. The other one was, if you're not elite, the bottom part of the graph, which we might be able to beat up, actually, unfortunately, hardware was moving so fast, why bother? So pre-2005, there's almost getting a doubling every 18 months in performance. All you have to do is sit back and wait for your new machine to arrive, and you get performance improvements. So why bother with this technology? So either the elite were going to be better than you anyway, or if they were not elite, the hardware was going to beat you. So we're going to get squeezed. We were going nowhere. Another part of the problem was, whilst we could get some good performance, we could do performance well for simple programs written in Fortran, say it's matrix multiplication. Not all code in the world is written in Fortran. In actual fact here, this is matrix multiplication. I know it looks mad by somebody would write it this way, but it's effectively written for DSP processors, the auto generation units, if you know that type of thing. In other words, parallelism is fragile. You can write stuff like this. You stick one pointer in a piece of code, and compilers go, I don't know what's going on. So in other words, it was unable to exploit the performance. And this must be the nadir statement I found out in 1998. Even if you assume that we've been working in this area since 1960s, you look at the performance compiler people have given us, it's on average 3% per year. Now that's back in the, until about 5 years ago, that was less than what we were getting from annual increments in our salaries, right? So compiler people, I'd say pre that date. So in other words, we weren't really earning our keep, while the guys in the hardware were getting 60% per year. So in other words, yes, another reason why compilers were failing. So at the end of the 20th century, we had parallelism was dead. We had parting of the ways. The smart people always, what do? They follow the money. The money went up to grid computing. So the applications, algorithms, the runtime people went up to the grid. The architecture people kept on following Moore's law, getting that 60% return. Well, us down here had to go and think differently. So we decided not to try and compete on the big supercomputing stage, but to look at maybe a different stage. And that different stage was the embedded stage, with small-scale computing. I think this is an advert for one of our groups here. This is Nigel Topman's Pasta group. They built this really cool small chip. So how do we make those things go better? So in the embedded systems world, there's little parallelism, but small improvements matter. If you can get the code size a bit smaller or the program a little bit faster, because you're going to replicate that on your phones or digital set-top boxes all around the world, small improvements get magnified by the number of consumers. So what we did back then in the community, looked at Fresh's optimization problem. Had it really been all solved in the 80s? And we asked the question, what is the optimization space? So if we looked at all those different translations I talked about, what's the best one? Can we look at that space? And it gave rise to the birth of two areas, one called iterative compilation, where we tune code, and one based on machine learning, which is where we're working today. And we tried to explain why we failed. So let's have a look at this. So the question is, why do compilers fail? We've had all these people doing all those research grants, and they got such poor performance, yet programmers seem to do very well. So what we tried to do is look at the simplest problem we could think of, which is matrix multiplication. I mean, I had a quick scan of this. There's over 500 papers on this area, just easy looked up via Google Scholar. There are many more out there if you dig a little bit deeper. So it's the most studied problem possible. So you look at the most studied program and try to see what the performance space would look like if we tried different optimizations and compare it to what was going on out there already. I want to ask the question, what does the space look like? So there are many, many papers saying how you should optimize this piece of code to get the best performance. And what we want to do is, actually, in fact, they have all these ideas. To what extent are they telling the truth? And that seems a very obvious question to ask, but it hadn't been asked at the time. So here's an example of a very old machine. And what we did here, we tried one transformation called loop unrolling, another transformation called loop tiling. And we plotted the performance of all these different bits of code and ran them on this machine. And here's the space here. The thing is, this space has got lots of local minima. It's choppy. It's got hills. It's got valleys. So it's very difficult to find the best spot. Our job really as compiler people is find the spot that's at the minimum. Now what happens is, once you look at graphs like this, you say, oh, I can see some structure. There's lots of valleys along here, lots of stories. But when you run it on a different machine, the space changes radically differently. And then when you change the program again, it changes one more time. So the structure is very hard to find in these spaces. In actual fact, so here's an example of the space there. We found the minimum. That last example goes across there. The minimum, another machine are up here. And look at the Intel machines, they're all over the place. So the key take-home point is that the space is hard, especially if the hardware changes. That's why we didn't do so well. So we've got an excuse. And we found is that all existing analysis, all of it was wrong on this most studied benchmark. So the stand back thing we realized at the end of the 20th century, we want evidence about things, not theory. Theory is useful in guiding ideas, but it's not an evaluation of a technique, it's just a guide to ideas. So there's been a massive cultural shift in the way we look at things since that days. And there's been two ways forward: searching the space to find the right answers, which are as accurate but slow, and another technique based on machine learning, which is try to learn the space and find the best things. So just searching, this is now known as iterative compilation. So you just search, there's a search example over here. You just try a program, try lots of different variations and pick the best. It's great, it doesn't require any clever ideas inside the compiler writer's head. There's no hardwired heuristics, it's based on evidence, not belief. However, it's expensive and you have to do it every time the machine changes. I just want to show you this little graph over the side here. We did that graph back in '97. This is Intel's version, just launched in 2013. So you look at the time for an idea from academia to eventually get into products. We're looking at about 16 years there. So it's so slow. Why don't we try something else? Rather than trying to search all the time to find the best example, why not use knowledge of prior searches? Why not use knowledge of other programs? So the idea here was, if I got a new program coming in I want to find the best optimization for, why don't I look at the ones I've seen before and use them as a guide? So if this program looks like E, maybe the best ones are around here. If you have program A, maybe the best ones are around here. Program C, got trouble, it's a bit difficult, that one, and D and E aren't so easy either. But the idea was not to keep reinventing the wheel every time, but try to somehow reuse prior knowledge. And this is kind of the simplest form of machine learning we describe here. There's much more exotic techniques than that. Well, we applied that, and we got some good results. So that's the space of all optimizations over there we could try, and all those dots are good points, or reasonable points. What we do is find little islands in the space, and if you show if you actually use our technique, random search after 10 evaluations will get you 32% of the performance available. Use the smart techniques, you can ramp it up to 79%. And generally, you get things 10 times faster. So machine learning can speed up search. Using prior knowledge can speed up search. Remember, the machine learning models are based on data. So real data can help you do things on new programs. So to summarize what we're trying to say in a kind of more visual way, this is the compiler writer's view of the world. We have these nice little algorithms stack up nicely. But in fact, if you look inside the machines, actually, they look a bit like that, full of lots of different bits and pieces that nobody really understands. So if you want to try and do something quite well with those type of machines, what are we going to do? Well, we're going to use, if you have enough data and you have the right model, you can automatically capture the behavior of something without having to delve deep inside it. And you can predict outcomes without knowing all the internals. The caveat is you need lots of data, and we're going to come back to that message a little bit later on. There's still people in my community who'd like to believe the world looks like that, but believe me, it really does look like that over there. So lessons learned. Handcrafted optimizations by clever people are doomed to fail because they're based on fiction. The world is not toggle blocks. I was going to regret going back there. Here we go. So let go of certainty. You don't know everything about what's going on inside that machine. Let go of it. So use dynamic analysis, statistical modeling, automatic prediction. Just use statistical techniques. Hardware underneath the hood is actually probabilistic. You've got random replacement inside your caches. You've got guessing happening by the branch predictors. So hardware is non-deterministic and probabilistic, so why shouldn't the software be as well? So in other words, you want to go from a logic view of the world to a more statistical world. Or more contentiously, I like to say, downward logic, upward data. Forget all the smart stuff, just give us the data. Right, so that's what happens in the embedded systems world. But what was going on outside our little embedded systems world where we're very excited? Well, parallelism came back with a vengeance. It is now cool again. So in 2005, sorry about this graph here, we basically were unable to keep on scaling the frequencies of these cores. And Intel was in a bit of a panic because you couldn't sell them anymore. You can't keep on ramping up the clock of your machine because they would melt. So we need to have some parallelism instead. This is a great statement by Chuck Moore from AMD. The industry is in a little bit of a panic about how to program these multi-cores. To make effective use, you need a PhD, which is great given that we've got a CDT in pervasive parallelism, so if any students want to come along, and we will give you a PhD, but perhaps we need more than 50 PhDs to solve the problem of programming in the future. So what are we going to do about that? Rely on Edinburgh to develop all the CDT students? Maybe you need some other approaches as well. And there was money in it, so guess what happened next? So the community all decided to chuck all that stuff again, and let's go for multi-core. All right? So that's what we're all looking at today. So we're all looking at how do we go around and program these new parallel machines that are available. So parallel computing compilers is one approach. Haven't we done this before? We're going to try and say, let's do it like we did last time, or we're going to try and avoid Groundhog Day and try and do things a little bit different this time around. So the question is, what's different this time around that we didn't know last time? And I'd like to, and if you can actually if you can learn from our mistakes, which we've seen before, and learn from the successes we had in the embedded world, can we translate them and make some use of those two things? So as Einstein said, insanity is doing the same thing over and over again and expecting different results. I like to think I'm a sane person, so we're going to try and do it differently than we did last time around. So what's different this time around? Well, the great thing, parallel computing is no longer an elite. It's not those tricky physicists you've got to keep happy. Never will, right? Mainstream people want to get parallelism out of your machine. So basically, it's easier to impress them. So you don't have to be successful. But also more importantly, there's more of them out there. So if you do impress any of them, there's more impact long term. Other big things changed. Big data, everybody's heard that word. It's a whole way we generate loads and loads of data out there from the web and other types of cloud-based systems. And from that, we can extract patterns of behavior. Could we use that technology for designing computer systems and compilers? Lots of data, automatically detect patterns and exploit it. That's, I think, the answer to exactly what we're going to do. So this was how we did the traditional way of developing compiler theory and papers. And I still see this in my job as a reviewer. Appeal to reason. This is a great idea. Look at the elegance of my technique. It's probably a set of equations look really nice over some simple terms. It's an elegant model by hand. It looks very nice in LaTeX. Find some benchmarks that fit your approach. Test your technique against your competitors or your friends, and iterate over your benchmark selection until you win. So in other words, you've got this type of approach, where it's model-driven with some nice simple maths underneath, and it's based on a paucity of data. However, the new approach is different. Select large benchmark, create a large optimization space. Analyze it. Is there any room for improvement? Can you do better than what's going on out there at the moment? If not, go do something else. Only then model automatically and properly test it by separating your test and your training data. So in other words, this type of approach, where the data drives the research and the model's the cherry on the top. So in other words, here's the take-home message I'd like to get to systems designers and parallel compilers and architecture designers. It's all about the data. You've got enough data, you have confidence in what your decisions are. If you're making the data up to fit your paper, you're not going to get very far. So whilst we like to talk about machine learning-based technology, it's actually a statistical model. It's really just a cherry, or in my case, a hammer. And you'll see why later on the top. And what we're really doing is going to an evidence-based approach to our subject. So this is a significant step in the maturation of the science when you use evidence to drive it rather than just appealing to reason or mathematics. So, data-driven modeling. We've got this tool now, and we're looking for some nails out there. So we've got a technology we think would be cool. Can we find any problems? And this is what the next half of the lecture is going to be about, me finding suitable nails I can drive down and beat the opposition. So I haven't changed too much from the other guys, but I'm trying to do it more honestly. So, machine learning is a solution. Well, it automates design. You stick a load of data into a box and out comes your answer. There's a bit more to it than that. Porting and mapping allows you portable mapping and parallel programs. It can adapt to change over any time scale. So in other words, you change the machine, you just relearn the model. You don't have to use any intelligence there. And it critically overcomes interfaces and models behavior. It doesn't need to know what's going on inside your Babel's tower over there. It just tries to work out how the whole thing works globally and then models it. And crucially, it separates policy and mechanisms, which are typically entwined in compiler design. We separate out what we do with why we do it, and then we can let learning technology take over and make the decisions for us. So the key question is, can machine learning help us with this paralyzation problem? So in other words, is it a nail worthy of driving into the ground? The answer, of course, is yes. So let's look at what the state of the art's like. So this is the compiler from Intel. It's been worked on since the 70s. And what we did, we applied it to a bunch of benchmarks. So these are programs all the way across here, that standard benchmarks here. And here's the performance improvement over one. Well, if you're really lucky on one program on a parallel machine that's got how many cores? 8 cores in this example. Intel's compiler will give you a massive 1.3 times improvement. You get it wrong, you're down around 0.06, massively slow. On average, after all those years of study, we slow code down on average. So there you go. That's not just me failing. That's a larger organization not doing too well either. But we've got lots of reasons why we're doing so well. So the question is, can we do better? Clearly, if we can do better, we should hopefully get at least above 1, not slow the machine down. Well, if you look at what humans do, those pesky people who are cleverer than us all the time, the actual fact, you look at the manual parallelization, they're on average 3.4 times faster than the original code. So there's a massive gap, room for improvement, so it's worthy of study. If there was no room for improvement, we'd go away and find another problem. That's the key message I'd like to get across. So why such poor performance? Well, it's fragile code. There's pointers everywhere. Compilers don't like them. Static LS finds no parallelism here, even though we know this is actually a parallel loop. There's indirect array accesses, there's reductions, there's pointer aliasing, dynamic allocation. All that stuff scares the hell out of a compiler. They say potentially two references will alias each other. They could then cause a sequential dependence. You better run it safely sequentially. Compilers are paranoid about giving you illegal code because maybe things will drop out of space if they don't behave correctly, so it's important you do correct code generation, but it misses that conservativeness, has lost us the opportunity for performance gain. Another reason is that sometimes you get parallelism available on some machines, such as Intel, but you run that same code on another machine, you get a slowdown. So in other words, whether you get performance not only depends on the intrinsic code structure, but the hardware underneath the hood you're looking at. So all we propose is a data-driven approach. So you start with sequential C, you do some analysis, you generate some code with some annotations, and then use machine learning to map it down to hardware. So use data-driven approach twice, one to discover parallelism and one to map it to the hardware. So we use profiling to gather evidence, not proof, of potential parallelism. We do lots of profiling and say this code is probably parallel. Then we use that knowledge and prior knowledge to determine how you map that down to hardware, how to chop it up into bits. And we ask the user to double check if we're safe, and we predict if it's worthwhile to run your code. So we applied all that technology, and what happened? Well, rather than getting a small slowdown, we got on average a 3.34 speed up over 8 cores. So if you just drill down to that graph here, this is the best a human can get, the grey one. That's what we got, the pink one. It's got 96% of the performance of a programmer doing this technique. So that's quite good. That was on one machine, the Intel. What about the other machine, the cell we were looking at earlier? Well, actually, manual parallelization, running those same codes on the cell, actually gives a slowdown. They're ill-suited for it. Using our technique, you get 2 times speed up on this code. The reason is the machine learning map has worked out when it's worthwhile to parallelize, and it's worked out when it's not worth the effort. So it's actually learned those techniques. So we've shown computing's parallel, and we showed that machine learning is a good technology to exploit that parallelism. However, it's a bit more complicated than that. It's actually parallel and heterogeneous. So if you look inside an embedded device, you kind of think maybe about 1 or 2 cores inside there, these A15s here. Actually, the hardware is a lot more complex than that. It's got Cortex M4s, it's got a graphics processing unit in there, it's digital signal processors, it's got a video accelerator. How are you going to program that is the real challenge we have to face. So one way to do that is to use a programming language called OpenGL that you can use for programming and increasing the performance of your graphics processing units. So that's been an awful lot of interest in GPU programming. And so what we did, we want to see whether we could use OpenGL to program such complex bits of hardware. Now, let's think about it. It's very portable, this programming, run on any GPU you have and other acceleration devices, but it's ugly. I won't show you the code. It's really, really hard to program, and performance is highly variable across machines. So what we did, we came up with this new technology that generates different versions. We take the original version of your code, and we generate some OpenGL version of it, which could go well on the GPU. But we also keep the old version here, which may run well on your CPUs. So you have multiple different versions. And at runtime, we choose which one's the best one based on machine learning technology. So in other words, we try to use the GPUs when they're likely to make performance improvements and use the CPUs when we're not too sure. So how did it work out? Well, we ran on 3 different machines, the Intel CPU, and we took one from the NVIDIA and ATI, their different versions of the GPUs. Important thing about the Intel ones, they're highly clocked versus the other guys, well, they have much less parallelism. So if you've got a very parallel bit of code, maybe your GPUs would work out well for you. If your code's a bit more sequential, you're better off with the CPU. So, showing, well, if you run all the benchmarks on the CPU, you get an average of 2.8. These are NAS parallel benchmarks. If you run them on the GPU, you only get an average 1.7. You get less performance. Sometimes you get a massive improvement. Other times you get a slowdown. Using our smart technique that chooses whether to use GPU or CPU, we get average 4.51 times improvement. Similarly, on the ATI, we got an average of 4.2. And that's about 92% or 97% of the Oracle. The Oracle is, let's look at all possible combinations and pick the best. So the machine learning technologies worked out actually when to use the CPU and when to use the GPU. So in other words, it's taking the worry out of you as a programmer when to put your code, let the system work it out for you. But you could argue, well, maybe you just generated junk OpenGL and you could do better yourself. Well, we took some benchmarks from SNU. This is in Seoul, National University in Singapore. They wrote all the code themselves in OpenGL. And if you compare their baseline OpenGL code, they're better than us. However, because we're smart and we choose which ones to use all the time, we're better than them. So using machine learning can help you choose between the stuff you generated on the OpenMP or OpenGL and doing the right thing. And this way you get a performance improvement over over the others. So the last technical piece I want to talk about before we go into the more wrapping up side is can we use this data-driven approach to explain behavior? So not just predicting the right thing, but if you do something, why do you get this performance? This is a question we always get from reviewers. Yeah, you may be better than everybody else. Yes, you may use a systematic technique, but why? And we always have difficulty explaining why. This piece of work tries to address that. So we have this compiler, takes in OpenGL, does some transformations to it, and then runs on 3 machines at the bottom. And the transformations are thread coarsening, stride optimization, and work group size. What they are doesn't really matter for us. The point I want to get over is the next slide here. It says if you get the right coarsening factor for some machines, such as the Cypress here, you get really big performance improvement. You try doing that on another machine, the Kepler machine here, you get a slowdown. So getting the right transformations is important, but it's difficult to get. And it depends on the program, it depends on the hardware. So we did something based on the previous slides. We decided to generate lots of data to see how we should do this. We did 43,000 experiments. Well, actually, I didn't do 43,000 experiments. My co-authors did 43,000 experiments. Took 17 benchmarks, 5 machines, and we run a whole bunch of transformations. And we tried to work out whether we could get some performance improvement out of that. So, actual fact, yeah, there's large potential performance. This is the baseline here. Before you do some baseline transformation, it's quite poor. You do all the right transformations, you get significantly greater performance improvement. So you get the right local group size, like work size, right coarsening size, you get great performance. So the question is, how easy is it to get that performance? Well, it's hard. So here's some violin plots. The dot here is the average point in the space, or the median point. So it means on average, if you're running this program here and you try an average transformation, on average you're going to get it slowed down. If you're a poor compiler writer and your boss has told you to try and improve the performance of this program, you've got real troubles, right? Only if you're very, 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 very lucky, you'll get back to the original performance, okay? In general, you're going to do very poor. So on average, it's hard to get the right optimization. And the space is quite tricky to understand as well. If you look at a different architecture, the i7, things change radically differently, right? Some benchmarks suddenly become very easy to optimize, but MV Cole is still tricky, and some benchmarks have really wide spread. If you're lucky to be asked by Intel to speed up their SGM code on their machines, you do quite well. The average is above the bar. Other codes you do very badly. So it's tricky to find good performance, and it's hard to explain why this is happening. If you look at the best optimization factors, on some benchmarks, you're best with, on some machines, 1 and 2 are quite good optimization factors. On other things, you see a much different spread of optimization factors going through the space. So trying to find the right optimization is tricky because there's a large numerical spread, and the right points are hard to find, and it depends on hardware. So what we tried to do is, could we analyze what's going on, so try and find some structure in all that complexity. And what we did is that we tried to work out the performance and the characteristics of the program code before and afterwards. We built a thing called decision regression trees. And what we found is on the Fermi architecture, you're able to reduce the number of loads, you get a good performance improvement. If you're unable to do that, you still could do quite well as long as you get the branches under a certain factor. Since then, Fermi's been updated to a new piece of hardware called the Kepler machine. And what we find, it gives similar performance, but it's much less forgiving of branches. You've got too many branches in there, you're going to get really slowed down to 0.34. So here's a way of analyzing our data to show you some insight of the actual hardware. On another machine, the Cypress, this is a VLIW machine. If you don't get here, where VLIW machines try to stick lots of instructions into one go, if you pack them nice and tightly, you can get really good performance. Pack them wrongly, it's going to slow you down. So would this insight give you some, would this analysis give you some insight for the new machine coming from AMD? Well, unfortunately, no. On the new machine from them, you have a very different one. And the reason is they completely changed the architecture inside the CPU. So any knowledge you may have had as a programmer about how to program these machines is suddenly violated when they change the architecture inside. You would never, any compiler heuristic you put in there would be wrong. This analysis shows you that and tells you where you should be spending your time and effort. And if you're unfortunate to have the i7, it's actually completely radically different, totally different structure, and actually loads don't matter, which goes against everything we've ever learned about the i7. So that's a rattle through 3 technical things. I'm trying to draw some more general views now. So what's the benefits of a data-driven approach to our subject? Well, it's evidence-based, not opinion, not how clever your maths are, not what your friends think, not how smart you've been in choosing benchmarks. It allows you to do oracle studies, find what the best you can do, so you can work out whether it's worth trying to do any more. We have a technique called beating random. You'd be surprised how hard it is to beat random. There's a famous, well, I won't say famous, there's a paper we compared ourselves to, and it was widely cited, and it's a very clever and elegant algorithm they put forward. If you just tried rolling a dice, you would have done better. Though, of course, they didn't do that experiment in the paper. And it allows us to separate test and training data. And the key point, it allows natural automation. We don't need clever compiler people anymore. We let the system do it for us. What are the challenges? Well, this is a classic big data diagram, I think, stolen from IBM's website. So these are some of the things you have to worry about. Volume of velocity, basically how quickly does data change. Well, machine learning can manage that. Variety, that's okay. The real problem we have is veracity. We totally rely on the data that we generate to build our models. So if you get some garbage data, you're going to get a garbage model. And that's too often a problem for us. Some pitfalls, signal and noise. We sometimes see experiments like this. Can you find structure in such things? We think when we run a program, we're going to see, we think that's the execution time. Actually, we've run it many, many, many times. See, it varies all over the place. Often you have a very clever model. The actual fact we've done is really overfitting. We've only got 10 data points. And we make this very complex model, but actually fact underneath the hood is there's a lot more structure there. One of our big ones is that we can rely too much on this modeling technique. It's magic, it's a panacea. We should look inside our black box sometimes. Correlation does not equal causality, and here's a good example of that. This just proves that actually fact Facebook were responsible for the Greek debt crisis. So here's the number of people in Facebook. Huge number, and here's the debt crisis. So they're clearly correlated. We need to close down Facebook and solve all our problems. There's an inherent mistake in that reasoning, but you'd be surprised how much of the papers we have in our area don't observe that mistake. So is machine learning a new silver bullet? Is it going to solve all our problems? No. It's a tool, not a hero. We still have to work across the applications down to hardware space. It's a mechanism, not a panacea. So, coming to some conclusions. Managing a heterogeneous many core is going to be the challenge for all of us the next decade to come. Handcrafted optimizations, the way we deal with compilers, is doomed to fail. We've got to stop it. We've got to let go of certainty using dynamic analysis, statistical modeling. So, we've heard this all before. Paralyzation is really important. Are we having Groundhog Day one more time? No, we think it's going to be different this time because hopefully we'll learn our lessons. So, data-driven, bright future is what we're hoping for. So, what do we want? Evidence-based change. And when do we want it? After careful peer review. That's what should be our challenge as compiler writers. So, if there's any industrials in here with too much money, there's a conference happening here in June. If you want, sponsors are welcome. Please see me afterwards. And I'd really like to thank everybody here who's done all the work for me. And thank you very much.
So what about going in the other direction, using your analysis to inform the people who are designing the microprocessors how to improve their microprocessor design?
That's exactly right. So what we're doing at the moment, there's a whole bunch of other work in the architecture space. And what you try to do is you try to explore the variation of your code on some hardware, and we've basically helped that to drive design in that space of hardware. Yeah, exactly right. It's
are you listening?
I couldn't comment at the moment unless the NDA is signed.
I'm a little bit worried about the fact that all your performance sort of peaks out at about, a factor of 2 or 3, and that's great. But I go run stuff on Eddy, and really, I want 1,000 cores, or I want my 1,000-core GPU, or I want my 50-core chip, or 64-core chip. I want to hit 32 at least of those busy. So I'm a little bit worried about peaking out at about 3 or 4 here.
So actually, what you should look is the Oracle study. What's the maximum you could theoretically get? So the key thing is so we're typically above 17 to 90%. So that GPU performance is 2 times better than an already parallelized version running on that machine. So it's already using massively parallelism. I showed things small scale, 8-core, 16 cores. The parallelization still will scale up. So the question is, does it scale up? Yes, it depends on the inherent parallelism in the machine. We've done small scale things, they're easier to run, but the technology is independent of that. So yes, exactly right. We have to show for large scale applications. But the important point though is think about who we're trying to get. We're not trying to get necessarily Hector running. full blast. They're the elite, right? They're going to be better than us. Many people have just got mobile phones with 4 cores inside, where if you could turn the processor off to save some power, that's a big win. So in other words, it depends what your optimization target is, but you're right.
So I perked up when you mentioned ML.
Yes. You would.
But then I realized it was the other ML.
Yes, yes.
So you'll know very well that Robin Milner and others here invented a programming language called ML.
Mm-hmm.
There's many descendants for things like F# that are actually used to write parallel and distributed programs.
Sure.
And of course, thinking hard about how to make something run in parallel can have advantages sometimes. So I was going to ask you about what the trade-offs are between the two MLs.
Well, actually, in fact, I don't think it's an either-or. There's a first stage you can do auto-parallelism discovery. We have this profile-directed approach, and that will discover parallelism. But there's only going to be parallelism that's available buried in sequential code. Long term, we want people to think parallel. And even when you think parallel, we want them to focus on the parallelism in the code, not understanding the intricacies of the hardware. So the machine learning is good at mapping high-level parallelism down to machine parallelism, and I think it's going to beat any human. Exposing parallelism, we've got a short stop approach using profile-directed approaches, but long-term, we want people to think parallel. So in other words, it's the two communities can come together. Those to design sensible languages, which people can focus on the high-level parallelism, and then we can take over all the grunt work, mapping it down to the hardware. So it's a win-win, not a competition.
Your slides gave examples of benchmarks and optimizing benchmarks.
Sure.
I was wondering how much progress you've made scaling this up to real programs and
That's interesting.
things.
So we live in a community, and that's a central problem, where we have a kind of a set of games you're allowed to play called benchmarks. And they have to be big enough so they test your idea out, but small amount that academics can write compilers and get things going. The real world is a bit more complex than that. So we've got some industrialization work, not done by myself, but others here, trying to look at larger scale approaches. So in actual fact, that's part of a technology transfer idea we're trying to do at the moment. The thing is, the concept will work, but the actual practice is hard, and you need real engineering to do that, right? And some people nodding their heads here. So actual fact, so yeah, that's the open question. We haven't solved all the problems. We've got some of the ideas, but we've got to take them to market and make it really work. So I'm hoping to find out the answer to that question. And maybe in another 8 years or whatever it takes, we might be able to come back with a better answer than that.
Thanks, Mike, for a very interesting talk. I want to ask you about Occam's razor. Mm-hmm. So you criticised the idea of simplistic but elegant solutions.
Sure.
And said that that was just kind of picking the data.
Yes.
Okay, but maybe you've sacrificed any notion of elegance and beauty for the kind of mechanized and rather grungy and difficult to interpret solutions to the problem. Have you kind of gone too far in the other direction, if you see what I mean?
So there's multiple answers. I don't care about the grunginess. If it works, it works. That's the truth. But if I was trying to be a bit more academic about the answer, I'd say, yeah, you're right. We should use Occam's razor. We should look at our models. If they're too complex, but we believe otherwise, we probably overfitted the data. We need to look inside the box. Just because we find some structure there doesn't mean it's there. We have to be on guard. My view about Occam's razor, if you come up with an elegant solution, let's try them head to head, see who wins. Whoever wins, wins.
Mike, hi. Thanks for the lecture, but I've got a simple question. Someone who works in this industry with this wonderful parallel code, how do you debug it?
How do you debug the code? Or the
parallel code?
Compiler code?
Yeah.
The code that compiler generates?
Because the worry that we have,
yes.
That with this compiler is wonderful, but we always worry when we put this, we got a fantastic sequential code that runs perfectly, but we got all these CPU and GPU, like you said, but we want to use it. But when we get a speed up parallel version, when we try to put it in, but people always question, what if it breaks in the field? How are we going to debug it?
Right, so there's a whole area about parallel debugging, parallel semantics and stuff. All I can say, that's beyond my scope of interest. That's an easy answer. But no, there's actually there's a whole parallel world about how to do software engineering, veracity and accuracy of compiler transformations. It's something. There's no easy answer for that. We need to have compilers that are accurate by construction. But one thing I often see, people run the sequential code and the parallel code and they compare the differences. This is based on the assumption the sequential code was correct in the first place. Now, how often is that the truth? So this is another question we should ask. People don't like change. They believe what I have now is correct. If I do a parallel version, it may be that just is correct. Both incorrect. If it starts to crash or whatever, you need better programming languages. C++ is not the place to start, and then you can have more guarantees about the safety of your code. But I'll go back to my original answer. It's not my problem.
One of the kind of charming things about Mike's talk, in case you didn't notice, was he had the list of team members at the beginning and at the end of his talk. And I think one of the things he hasn't been talking about, because it's not that kind of a talk, is about what he's been doing over the years, leading ICSA, the Systems Institute. And Systems Institute is actually, I think, more than many institutes that I've seen here and in different places. It really has that kind of, it does have a kind of team mentality to it. It's very well organized. It does that kind of thing, perhaps because it has to, because it's systems type stuff. But over the years, it's really grown. And now when you look inside the Systems Institute in informatics, it's doing real stuff. There are products that you either have used or will use that have things in them that have been either conditioned or were specified by the Systems Institute. And it's not an easy thing to do. Systems is not an easy thing, an easy trick to pull off. So I think it's an amazing feat to have grown that so much over the time. And choose your measure. It has grown really an awful lot over that since you got your professorship. I don't know whether that's got anything to do with it at all. I couldn't say. So I think on behalf of us all, because of how that's changed the way that the complexion of informatics and how it's permeated, interacted with other things and machine learning and other areas, I think we should all thank the Systems Institute and especially Mike for all of the great work that we've done in transforming that particular area of informatics research. Thank you very much, Mike.
You're welcome. Thanks, Dave. Thank you.
This production is brought to you by the University of Edinburgh.